Good morning, everyone. Happy Monday. How's everyone doing today? Welcome to 2022. Welcome. Let me know how the stream looks too. So, just as a intro, so my name is Marissa. You can just call me Marissa, that's fine. And I'm really excited to be teaching Chem 105 this quarter. And so, a couple things I'm doing differently is I've always used Twitch in the past to stream. I'm trying YouTube just because I can sign up for a new YouTube channel, and I think that's generally friendlier for the general population, but I'm open to suggestions if people prefer like Twitch over YouTube. I'm just trying to keep videos consolidated in one place for future viewing. All right, so let's go over the syllabus. And if you have questions at any point, this is why I do it live. Just type your questions in the chat or just say hello if you're here. So if we go over to Blackboard, everything should be there. So I have a link to the syllabus. So the syllabus is over here. And so you probably got my email. We'll be having an online lecture at this YouTube channel, and then lab will be in person on Wednesday on the Medford campus, HCC building, otherwise online. So if you can't make it in person, which I completely understand since I think there's some last minute changes to the schedule, all the lab materials will be here. I haven't uploaded anything yet. I'm in the process of kind of reworking and retweaking the labs for this year. So I'm really excited to have y'all kind of help me test that. But I'll post at least lab 1 here. And then this first week I'll make a video of it. So if you can't attend, you can watch the video. But actually this first experiment that we're doing is going to be saponification. So making soap. And actually you could do that at home if you wanted. And then, so the other thing I do is, so this course is kind of designed to be self-taught in a sense. I wouldn't necessarily advise it because we'll be going over things in the live lecture, but just for your reference, so we'll just check out this first chapter. So down at the bottom, I have all the links to these old lectures with some PDFs and lecture videos from another instructor. And I will always post here. So these are where my current lecture notes are. So I make them available in both the OneNote format. So you do have to have the full desktop version of OneNote to open up this OneNote package. But I also make it available as a PDF if you can't open that. So now just looking over the syllabus together. So I try to make myself really available too. So this is a relatively small class, but really the best way to reach me, if you can't reach me physically, is to set up an appointment with one of my virtual office hours. So I, again, make myself available pretty much all the time. So I'm available after class for office hours. Then I have some in-person office hours if you happen to be in the Medford area. Otherwise, again, by virtual. And so we'll be continuing off of Chem 104. And so Chem 104 kind of laid the groundwork, and then now we'll go into nuclear and organic chemistry. And so book is still the same GOB book, this general organic and biological chemistry. The lab manual will be available online. If you're doing the in-person lab, you do need some goggles, so you can buy those at the bookstore on campus. And then please wear your long pants, closed-toed shoes. And then don't forget your face mask. And the gloves will be supplied. I think that's roughly it. So the other caveat is just you're expected to complete 70% of the labs. And everything else. So the other thing you'll want to check out is a schedule of assignments. Everything is there. So the only assignment that is missing, I'll probably make an announcement about this, is it's under the Welcome to CHEM 105. And then I have a welcome assignment. And it's really easy. It's just, check in. Are you here? And I've already been emailing many of you, so I don't expect any difficulties with this. All right. Any questions, comments, concerns before we get started with the lecture? And so again, feel free to type your questions at any point in the chat, even just saying hello. That's what this chat is for. All right, so let's start chapter 10. So chapter 10 is kind of, I feel like it's a wrap up of fall quarter. And let's do a quick reminder. So we had learned all about atoms in fall quarter in Chem 104. Sorry, my cat's here. Cats are always biting cords. So we had started off with the atomic structure back in fall quarter. So we had learned that atoms were made up of protons, neutrons, and electrons. And of course, the proton kind of made up the identity of the atom. So of course, we learned that this proton corresponded to its atomic number, which of course corresponds to the element on the periodic table. And then we learned that neutrons, of course, help make up the mass. And just a recap, so it was, right, protons plus neutrons equals our mass. So that was our total mass of whatever atom we're looking at. And protons, of course, were positive. Neutrons, no charge. Electrons will just go essentially massless. Simply because they're much, much smaller. And of course, negative charge. And so we want to focus on isotopes. And I believe we covered this, but again, just to recap. So isotopes are elements with a varied number of neutrons. And so just like we've stated before, so all atoms of a given element have the same number of protons. However, they don't necessarily have the same number of neutrons. And so we can see this from our example here of neon. And so just to recap what this all means, so we have neon 20, neon 21, neon 22. So these are all different isotopes, so they're all neon. And so recall that this number up here, so this is our atomic mass. So this is telling us the total number, or the total mass number. And so now we would just have to determine the number of neutrons. So we're comparing neon 20 versus neon 21 versus neon 22. And so, of course, they all have the same number of protons. That's the number reflected there. Also, its atomic number. So it has to be 10 since it's neon. So again, change the number of protons. We change the identity. We are actually going to be looking at reactions that change the identity, those nuclear reactions. And so now we can determine the number of neutrons in each one of these by just subtracting. So we have our mass, so 20 minus 10, so minus our number of protons. So this would give me 10 neutrons for neon 20, 11 neutrons for neon 21, and then 12 neutrons for neon 22. And so there's a couple of different ways to represent this. So again, this is kind of the most common that you'll see with our chemical symbol, of course, and then atomic number in the bottom left, mass number upper left. And so the other thing that we can note is, of course, the natural abundance. And if you recall, adding all these, so taking the mass, multiplying by the natural abundance, and adding them all together will give you what's called your average atomic weight on the periodic table. So again, just recapping, looking at neon. So the molecular weight of neon here is 20.180. That doesn't mean that one individual neon necessarily weighs that. That just means the average molecular mass is that. And so you could determine that from taking this natural abundance. So converting this to 8%, so 0.9048 times 20 plus 21 times 0.0027 plus 22 times 0.0952. So that's how you would get that number. Put my calculator there just so we're ready. So then what is radioactivity? So let's just define what radioactivity is. So radioactivity is just the release of high energy particles and or high energy electromagnetic radiation from the nucleus of an atom. And atoms that eject particles and or energy from their nucleus are referred to as being radioactive. And so what we find is that there are just certain combinations. So let's just kind of again compare for a second. So you're probably familiar with carbon 12, and there's also carbon 13, and then carbon 14. Anyone know what's special about carbon 14? So carbon 14 is unstable, or we would refer to it as radioactive. And so scientists aren't really sure what makes certain isotopes stable or unstable. It seems to have something to do with like a ratio of, the protons to neutrons, but there's also kind of stable masses and so forth. So we're not trying to look into that today, but I just want to compare. So carbon 12 has 6 protons, 6 neutrons. Carbon 13 has 6 protons, 7 neutrons. And now carbon 14 has 6 protons, 8 neutrons. And for some reason, this is now unstable. And so this would cause carbon 14 to decay and be radioactive. And so we'll look at what that means. And so radioactive decay involves the nuclide emitting particles and or radiation. So again, this carbon 14 particle would then break down. And so the parent nuclide, this is the nucleus that is undergoing radioactive decay. That's the parent. So that would be like your parent sample of carbon-14. And then the daughter nuclide is the resulting or new nucleus that is formed. And so just fun trivia. So nuclides with 84 or more protons are radioactive. So if we go over to our periodic table, so starting after polonium, all these tend to be radioactive. So if you remember, radium, francium, all these are radioactive. So you can kind of note that. That's a bad radioactive symbol. That looks like the peace symbol instead of radiation. So let's look at the types of decay, the types of radioactive decay that can occur. So the first type that we'll look at is alpha decay. So alpha decay is going to be, it's when you have a helium nucleus released. So let's zoom in on this here. So this helium nucleus, this is called an alpha particle. And so it occurs when your unstable nucleus emits a particle of 2 protons and 2 neutrons, aka our alpha particle. So let's look at our equation here. So we started with uranium 238. So that's our parent nuclide. Then we have our reaction arrow to show that it underwent a nuclear reaction. And then, so the other nice thing, and we'll talk about this further, but when we write these equations, we have to make sure that the total masses all add up and then the bottom numbers add up. And so what I mean by that is we started with 238 over here for our total mass. And so that means that these numbers, 234 and 4, should add back up to 238. So that's what helps you determine kind of what your product is. So you could say we have 238 uranium and it's going to undergo alpha decay. What's the product? Well, you can determine that by, if it's alpha decay, we know it's losing this helium nuclide. So you could subtract, so 238 minus 4, that gives you 234. And then 92 minus 2 gives you 90. Then you can go to your periodic table, look up 90. Okay, that's thorium. So that's going to be my product there. And so alpha particles, they are considered kind of the least dangerous of the radiations. So they're the least penetrating. So protection from alpha decay is going to be like a piece of paper or a cloth. So all that can stop those alpha particles. And so again, we see that atomic number decreased by 2 and our mass number decreased by 4. Just pausing for any questions or anything. Questions, comments? The next one we'll look at is beta decay. And so beta decay is when you have a beta particle is an electron-like particle that is emitted from a nucleus when a neutron in the nucleus transmutes into a proton, which remains in the nucleus, and a beta particle. So let's kind of look at this mathematically, what happens. So you have a neutron, And again, this is where your math kind of helps you because it can be kind of confusing. And so this beta particle, sometimes you see beta decay, like negative beta decay, by the way. And so this means that we have -1 on our atomic number. So our atomic number is decreasing. And that's kind of balancing out that proton that's emitted. So notice -1 plus 1 gives you back to 0. And then this is going to be massless, though. So our mass goes into that proton that's emitted. So there's our beta particle. So again, just represented by 0, -1 beta here. And so it emits an electron-like particle, so that makes sense. So again, it's massless but has a negative charge. So a beta particle is now 10 times more penetrating than an alpha particle, but only has half the ionizing ability. And so again, this isn't that dangerous, so it can be protected from like a heavier clothing. And so looking at our example here, so this is actually the decay that carbon-14 undergoes. So we're discussing carbon-14. So we could say beta decay for carbon-14. And so to determine this, we start again with our parent nuclide, carbon-14. And then they have told us that carbon-14 undergoes beta decay. And so there's a couple ways to solve it. So for me, if they're telling us beta decay, I'm going to write my symbol for beta. So our massless kind of electron-like particle. And then we need to balance it. So again, my upper numbers, my total mass numbers have to still equal 14. And so this is 0. So whatever my new product is has to have a mass of 14. And then we have to balance this -1 that was created. We have to get to 6. And so keeping with our principles, so again, the answer would be 7. So 7 plus -1 gives us 6. Now we can look up what element is this. So of course it has an atomic number of 7. So that leads us to the identity of nitrogen. Any questions on that one there? So now we have positron emission, but sometimes I see this written as like beta decay positive. So just be aware of that. And so as you might imagine, this positron is kind of opposite now from that beta decay. And so where we had kind of a massless negative charge, now we have a massless positive charge. So this is called our anti-electron. So that makes sense. It's kind of the opposite of an electron. So mass of the electron, but opposing charge. And so these are similar to beta particles. Again, that's why you might find them colloquially referred to as positive beta decay. So they have similar properties to beta particles. And so the positron is formed then when a proton transmutes to a neutron. So this would be in the nucleus. And then balancing it out, of course, we emit now that positive electron-like substance. So then looking at our example reaction here. So we're starting with phosphorus 30. So this is radioactive. And if we were to say that we know it undergoes positron emission, we could write our symbol for a positron. So that's 0 with a +1 charge, an electron here. Then we would balance the masses. So it would have to be 30 for our mass there. And then we have to balance it. So 15 is equal to x plus 1. So then that's how we have 14 there. And then, of course, 14, atomic number 14, corresponds to silicon. And so we know that 30 silicon would be our product, along with our positron emission. So kind of the last one that we'll look at is gamma emission. So gamma is going to be really high energy. So maybe you remember from your electromagnetic spectrum chart that gamma is extremely high energy. And so gamma emission is really interesting. So these are high energy photons. And with gamma emission, there's no loss of particles from the nucleus. So there's no change in the composition. So same, let's highlight that because that is a little odd. So same atomic and mass number. And so the symbol to reflect that is going to be 0, 0 with this little gamma symbol. It's like a curly Y almost. And so gamma rays are the least ionizing but have the most penetration. So this is what will damage you and harm you in, like a nuclear reaction. And so you would have to, hide behind lead plates or thick cement walls, kind of like they do in the movies, right? That's always how they somehow magically escape the nuclear disasters. They hide in a lead fridge, but of course they don't address that the radiation would still be there after the fallout, but that's okay. And so this gamma emission, again, that's what is going to do the dangerous. This is what killed people with Hiroshima. And so the gamma emission generally occurs after the nucleus undergoes some other type of decay and the remaining particles rearrange. And then again, extremely high energy, so damaging. So this is now our overview. So alpha decay, beta decay, gamma, positron emission. And then the only one that we didn't talk about because it's not in your book, but it's on this chart, is electron capture. We can just go over it briefly. I wouldn't expect to see it, but just in case you do see it somewhere. So electron capture, this just follows similar principles of what we've been discussing, just all the balancing of our mass and of our atomic numbers. But what happens here is, so you have your proton inside your parent nucleotide, and then you have an electron. And so that electron gets captured by that proton, and so they merge together. And so that proton becomes a neutron. And of course, so the mass, right, would be unchanged. But all you're just doing is adding that negative charge. So that cancels and decreases your mass number for your product there. So notice your parent here, so 92 ruthenium plus an electron capture. So that proton becomes a neutron. So your total mass is unchanged, but then your protons decrease from 44 to 43. So let's do some more practice with these nuclear equations. And so like we were kind of going over, all these processes can be described with these nuclear equations. And then the key point, which was helping us determine our product, was that atomic numbers and mass numbers are conserved. And so like we were saying, the sum of the atomic numbers on both sides must be equal, and the sum of the mass numbers on both sides must be equal. And of course, this conservation can be used to determine the identity of the daughter nucleide if the parent nuclide and the mode of decay are known. So we saw that with uranium, so we knew it was alpha decay, so we could determine that 234 thorium was our product. So let's do some practice together. And so the first one, write the nuclear equation for the alpha decay of radon 224. So I'll give everyone a little time for that. All right. So let me know if you need more time or put your answers in the chat while I start going over it. So let's approach this together. You can also let me know how you approached it. And so it says radon 224. Well, I don't know the atomic number of radon, so let's go look it up together. So radon is 88 there. Oops. So 224 radon. And it's going to be alpha decay. So we know we're going to be losing that helium particle. Now we just have to determine kind of who's missing. And since our total masses have to add up, so 224 minus 4 gives us 220. 88 minus 2, so it gives us 86. And so now let's look at what element 86 is. So 86, that's going to be radon over there. Good. Just checking for questions. So let's try the next one. I'll give everyone a few minutes. All right. So once again, we're looking at alpha decay. So I'll start off with what we started with. So polonium 216. I need to go look up polonium. Oh, there it is. So atomic number of 84. So again, alpha decay. So I know I'm going to be making that helium particle. Now we just need to determine the rest. So 216 minus 4 there. So that gives us 212. 84 minus 2. That gives me 82. And then going to my periodic table, looks like that corresponds to lead. So that's our product there. All right, try the next one now. So now we have beta decay. So what would that look like? All right. So beta decay. Always remind ourselves what that is. That was kind of like our negative, kind of like our electron-like particle. So let's see. So this is 249 berkelium, I believe. So BK, berkelium. So that's going to be 97. So beta decay emits that electron. And so our mass will be unchanged. Oops. And then recall that they have to add up, all that the atomic numbers have to add up. So we have a negative 1 there, so we need 98 to balance it out. So 98 plus negative 1 gives us back to 97. And let's check. So that's going to be californium that it's making. As you can probably tell, these are synthetic elements, and you can, guess either where they were discovered or what they were named to honor. Hence why those names suddenly get weird. And I forgot the abbreviation, CF. I was going to put CA for California. There we go. And then last practice of this, so write the equation for positron emission in oxygen 15. Okay, so let's look at this. So oxygen. So 15 oxygen, 8 for our atomic number. And then so positron emission, we said that was the opposite, right? Where it emitted that positive particle. You can always double check yourself, right? Positron emission, there we go. So that's our positron particle. So now we can just balance it. So our mass doesn't change for other product. And then, so by conservation, so it's going to have to be 7 here, because 7 plus 1 will give me 8. So it looks like that's going to be nitrogen. So we get nitrogen 15 there. Excellent job. Any questions on these or how to approach them? So hopefully they should feel really straightforward. Again, I would kind of reference you back to this ending here. And this will kind of help you figure out how to balance your equations, which is, really the hardest. But if this is the hardest thing you have to do, I think that's not too bad. So now let's look at kind of, well, why else do we care about this radioactive decay? And so where have you heard of radiation being used for? Especially maybe it's kinetics. It goes back to that carbon 14 too. So carbon 14, that's typically used to date like organic materials. And so how it works, and so you can see this here, is so the rate of change in the amount of radioactivity is constant and is different for each radioactive isotope. So meaning we have our parent nuclide and then it's decaying at a certain known time. And so this particular length of time, aka a half-life, is required for each nuclide to lose half of its radioactivity. And so that's what they say, you know, if we have a half-life of something, half of its parent material will be gone in that amount of time. So the shorter the half-life, the more nuclei decay every second, aka the more hotter the sample is. And so this is an issue for some of the like synthetic elements. So we were just discussing how scientists are working to, you know, make synthetic elements and heavier elements. But if you notice, some of these masses are like unknown or in these weird brackets. And that could be because they're unstable, so they just decay before you can even get an accurate mass. And so the other interesting thing is that the radioactive change is not affected by temperature, aka radioactivity is not a chemical reaction. So we've kind of looked at that. So remember, chemical reactions are just rearranging atoms, but now with these nuclear reactions, right, we're changing the identity of the atom. And so this is the only time you're going to be doing that. And so let's look at these kinetics because these are useful. So you won't have to do too much math in here. And, you know, this lecture will kind of go a bit beyond the scope of your book, but I think that we'll keep it simple enough and it's useful. So we have our rate here. So rate is just whatever your rate is, K times your N. And then integrated rate law would just be we take natural log of some N at some certain T over our initial amount is equal to negative K, which is our rate times RT. And then the equation for half-life, since it's first order, is equal to this. So our T half-life is 0.693 over K. And so, you know, people have determined the half-life then of various elements. So for example, going back to carbon 14, since that's the one that's again used for dating, it has a half-life of 5,715 years. So you can use carbon 14 to date samples. So that's what they do. And so living organisms should have like a certain ratio on carbon 14 to 13 to 12, you know, depending, since there's like a certain natural abundance of carbon 14 that gets integrated. But then once that organism dies, the carbon 14 will start decaying. And so you can measure that ratio of carbon 14 to the other isotopes of carbon 13 and then to determine an age. So let's look at a sample here. And notice, right, you have thorium, uranium, so these are much longer half-lives. You could do different dating. So that's how they do different dating for everything. So looking at plutonium-236, this is an alpha emitter with a half-life of 2.86 years. If a sample initially contains 1.35 milligrams of plutonium, 236. What mass of plutonium 236 is present after 5 years? So we have to determine. So we have our formulas here. Let's write. So half-life, 2.86 years. So we want to know how much is present after 5 years. Sorry, totally blanked out for a second. We have our natural log of NT over our initial sample is equal to negative KT. So if we want to know how much is present after 5 years, we have our T here. So T, 5 years. So we need to determine our rate. So kind of how many half-lives. And then so our N initial is 1.35 milligrams. Let's revisit this. So let's revisit this for a second. So effects of radiation on life. So radiation has high energy. So enough energy to knock electrons from molecules and break bonds. And so this energy transferred to cells can damage biological molecules and cause malfunction of the cells. And so, of course, acute levels of radiation over a short period of time can kill large number of cells. So this could be from a nuclear blast or exposed reactor core. So, of course, this can weaken your immune system and lower your ability to absorb nutrients or cause death even. So chronic risks can be genetic defects and cancer risks. So low doses of radiation over a period of time can show increased risk for development of cancer. And so low doses over time may damage reproductive organs and lead to sterilization. So this is why, if you go to the dentist, they always make you wear kind of those lead garments. And so measuring radiation exposure So you can measure it by a variety of different ways. So there's a Curie amount that CI is an exposure of 3.7 times 10 to the 7 events per second. So no matter the type of radiation. So you can measure radiation using a Geiger counter. And so this will be our first lab where we do that. And so the gray measures the amount of energy absorbed by body tissue from radiation. You can also have rad. And so REMS is red row antigen or equivalent man. So this is also another way to determine how much exposure you have. All right, so let's go back to that other problem. So we have our rate law. And so the other type of math that I want us to see, well, we'll revisit this. So let's revisit. But the other thing that I wanted us to look at is just kind of graphically how much happens in this half-life. This chapter is pretty. So before we look at this math, let's just look at it more simply. So if we have, starting at 100% of our parent, and then after one half-life, now would be 50% has decayed, 2 half-lives, 25, 3, kind of 12.5%, 4, 6.25, etc. You can see that the amount of material decreases really rapidly. So let's look at this one. So first we have to determine is how many half-lives have we done? So if we take 5 divided by 2.6, or 2.86, now we have how many half-lives we're going to be going through. So ln of nt over n0 is equal to 1.75. So now e to the power of both of these, kind of solve. So now nt over n0 is equal to 5.7. Something looks funny here. Okay, we'll revisit this. So I don't want to rush through the whole chapter either. Oh, so let's look at various sources of radiation. So we have, so remember you can get radiation from plane rides. So this is, 0.5 micro rems per hour. And then just comparing, so terrestrial radiation, radon gas. So this is your biggest source of radiation kind of in your home, is this radon gas. And so this can accumulate over time. So that's what those test kits are for. Chest x-rays. All these can give you, of course, high doses. Building materials. So of course we can also use radioisotopes in medicine, which many of you may be interested in. So you could use, xenon 133 to kind of visualize the lungs. You can use iodine to treat hyperthyroidism. Phosphorus can treat cancers. You have it depends on the nucleotides. So different nucleotides are used for different applications. So thallium is good for heart function. Technium is good for visualizing gastrointestinal bleeding. So pretty interesting. And so these radio tracers can be measured by the amount of element absorbed by the tagged isotopes. And we also have a PET scan. So now you can know that PET stands for positron emission tomography. And of course, this can do brain scans. So again, a lot of these different radioisotopes are used for cancer treatments. And I'm sure some of you may know or be familiar with this. And so it depends on the radiation. So of course, with all of these, as you just want to be able to target the radiation as much as you can without damaging the good cells. So non-medical uses of radioactive isotopes. So they're in your smoke detector. They can be used to sterilize insects, food preservation, or just tracing following a tagged atom. And then chemical analysis. You can also use it to authenticate like older pieces of artwork. Crime scene investigation, corrosion of thickness of materials. So all sorts of different applications. All right, let's see if I can do this without screwing it up. I apologize. It's Monday. Let's start over here. So we have to determine our K. So we start with our half-life. So going back to our problem. So this has a half-life of 2.86 years. And so we're starting with 1.35 megs. How much is present after 5 years? So let's start with K. So we're starting so let's just plug in. So So I'm starting with 1.35 megs over 2 is equal to 1.35 times E KT, where T is our half-life, so 2.86. And so now we need to solve for this equation. So now we get, so I'm just dividing all this. So 1/2 is equal to E times K times 2.86. Whoops. Sorry. Running out of space. So 1/2 equals E K times our T. Do the natural log of both sides. So this gets rid of our E. To just give us K times 2.86. And so now we just need to plug in some stuff. So natural log of 0.5 divided by 2.86. That gives us our K. So negative 0.24 or so. So now we can plug this back in. So now we can plug, everything into here. So natural log of n over nth time is equal to, so now we have K, negative KT. So T was 5 years. Now we have NT, or N0, is equal to 0.24 times 5, since those negative signs canceled out. And our initial rate was 1.35. So now this should make more sense. So times 5. Now just multiply. Man, I keep doing something wrong here. Oh, because I didn't take the natural log of this. That would help. Sorry, math errors galore. There we go. That makes a lot more sense. Sorry, I apologize. So take this to the e power. Negative kt. Let's try this again. So y is equal to ce kt. E power of negative 0.24 times 5. So times our original value be our answer. So then you will be left with 0.4 milligrams. So again, this is a bit beyond the scope of the course, but you want to be able to do is kind of identify, how many half-lives and the decay. So what we were discussing here. So, 1 half-life, 50%, 2 half-lives, 25, 3, 12.5, and so on. If we do any of these in class, we'll do some more practice on Wednesday to make that really clear. All right. So I feel like we've mainly gone through this chapter. Let's see, let's just finish up this chapter here. And then Wednesday we can do more review and go over homework. Which I apologize that this chapter's short. So we have the last part is fission versus fusion. So fission, this is what we're familiar with. This is nuclear reactors where one large nucleus splits into two smaller nuclei. Versus fusion. So this is what the sun does. Let's just write this. So nuclear reaction versus the sun. And so the sun does that, so it smashes smaller nuclei together to make larger ones. And so both fission and fusion release enormous amounts of energy, hence why there's a lot of research into the topic. So people are working to make fission better. There's actually a lot of research. So going back to this reaction, actually, so this is what a nuclear reactor does. This decay of uranium to thorium, but then we had an issue of this thorium byproduct, but now they're finding how to use thorium in nuclear reactors as well. So that's really cool. And so this fission chain reaction occurs when the reactant in the process is also the product of the process. And so this is, again, kind of how a bomb occurs as well. So if you're trying to make a bomb of 235 uranium, plus you have this neutron here, and then it's going to create this chain reaction. So in a bomb, you would have two what are called subcritical masses. And then, of course, once they collide, that's, when the bomb hits, the barrier separating those two subcritical masses is broken. So now you have a critical mass, which leads to this kind of out of control nuclear reaction. And so the minimum amount of fissionable isotope needed to sustain the chain reaction is called a critical mass. And so nuclear reactors are run like just under this critical mass. So they just want to keep it just going. And so fissionable isotopes are 35 uranium, 39 plutonium, and 240 plutonium. And so natural uranium is less than 1%. So they have to enrich it. So it's about 90% for weapons grade and 3% for reactor grade. Okay, let's actually finish this up on Wednesday. We'll finish going over nuclear power because I don't want to rush this necessarily, but I want people to think about, nuclear power, alternative energy, and maybe other such topics. So let's keep this for Wednesday. So let's go ahead and stop here. So thoughts for Wednesday. So how does nuclear power compare? And I'm not expecting, a thesis or anything, but just start thinking about the differences in all these energy sources. And so we'll discuss it on Wednesday. I want to hear kind of thoughts and comments. If you can't make it live, I'd love for you to send me an email just so I can hear your thoughts so I can discuss them. So let's go ahead and end the stream here for today. So like I said, we'll do some more practice problems on Wednesday to give you all a better idea of what you should be studying for and finish up a bit about nuclear power. All right, thank you so much for coming to the first lecture. Sorry for the bit of math confusion for a second, but we'll get everything clarified for Wednesday. So thanks again. I will stick around in the chat in case there are any questions. Otherwise, see everyone on Wednesday.